Welcome to Lesson 2 of our Cyber Safety module for ELN 260, Programmable Logic Controllers. In this lesson, we will focus on PLC network vulnerabilities and protection. PLCs are essential in industrial automation because they control real machines and processes. But once PLCs are connected to other devices and networks, they also become part of the cybersecurity picture. In this lesson, you will see how network communication supports industrial control, how vulnerabilities can appear, and what we can do to reduce those risks. Now that we have introduced the lesson, let's begin with the big idea behind PLC network risk. PLCs often communicate with sensors, actuators, HMIs, and engineering workstations across industrial networks. This improves automation, coordination, and control, but it also creates cybersecurity risks. If communication paths are not protected, attackers may intercept data, send unauthorized commands, or disrupt industrial processes. In other words, the same connections that make systems more capable can also make them more vulnerable. Now let's look at the objective for this lesson. This lesson explains how PLC communication protocols such as Ethernet/IP and Modbus support networked industrial control. It also shows how unsecured connections can lead to cyber incidents and why data flow and access points must be protected. As we move through the lesson, keep in mind that communication is essential in modern automation, but those connections must also be secured. To understand that better, let's start by looking at where PLCs fit in a networked system. A modern PLC is usually part of a larger control system. It receives signals from input devices, processes logic, and sends commands to output devices. It may also communicate with HMIs, SCADA systems, drives, remote I/O, and engineering computers over a network. This means the PLC is not working alone. It is part of a much larger environment, and every connection within it can affect both performance and security. Before we go further, let's review the role of input and output devices in that system. Input devices send information into the PLC. These may include sensors, push buttons, switches, and temperature transmitters. Output devices receive commands from the PLC and carry out actions. These may include motors, valves, relays, alarms, and indicator lights. When these devices are networked, the data paths between them become possible attack points. That is why understanding the flow of information is so important in industrial cybersecurity. Now let's look at two common protocols used in PLC communications. Ethernet/IP is a widely used industrial Ethernet protocol that supports communication between PLCs, input/output devices, drives, and other automation components. It is based on the Common Industrial Protocol, or CIP, and is designed for industrial control and information exchange. Ethernet/IP is common in industrial automation because it supports efficient communication across network devices. However, like any communication protocol, it must be used securely. Another common protocol you should know is Modbus. Modbus is one of the most common industrial communication protocols. It is used to exchange data between control devices and can operate over serial connections or Ethernet networks as Modbus TCP. Its simplicity has made it very popular in industrial systems. At the same time, that simplicity can create security concerns if it is left unprotected. This is an important reminder that convenience and compatibility do not automatically mean security. To understand why protection matters, let's look at the main problem with unsecured industrial protocols. Many industrial protocols were originally designed for reliability and interoperability, not for modern cybersecurity. If communications are not protected, attackers may be able to read traffic, identify devices, alter data, or send unauthorized commands. This means normal control traffic can become an attack path. In industrial systems, that can lead to consequences far beyond data loss, including process disruption and unsafe operation. To see why that matters, let's walk through how data moves in a PLC network. In a typical PLC system, sensors send input data to the PLC. The PLC processes that data using its program logic and then sends output commands to field devices, such as motors or valves. Operators may monitor or control the system through an HMI, while engineers may connect through programming software. Every step in this data flow must be protected because each step represents a possible point of attack or interference. Now let's identify some of the most common weaknesses in these networks. Common PLC network vulnerabilities include default passwords, shared accounts, unsecured remote access, lack of encryption, poor network segmentation, unpatched engineering workstations, and unrestricted USB use. These weaknesses make it easier for attackers to access the network or manipulate PLC communications. Many of these problems are not especially advanced. They are often everyday issues caused by weak practices or poor security controls. So, what might this look like in a real incident? A cyber incident can occur when an attacker gains access to an industrial network and sends false commands or changes controller behavior. In some cases, the attacker may first monitor traffic, learn how the process works, and then interfere with PLC logic or device communications. The result may be downtime, equipment damage, or unsafe operation. This is why industrial cybersecurity is not just about protecting information. It is also about protecting real equipment and real processes. Here is a real-world example of PLC cybersecurity issues. In 2023 and 2024, attackers targeted internet-exposed Unitronics PLCs used in critical infrastructure, including water and wastewater systems. Many of these devices were vulnerable because of weak security settings, including default passwords. This case is important because it shows that attackers were not just targeting office computers, they were reaching actual industrial controllers. In some cases, systems were defaced, and operators switched to manual control to reduce risk. The big takeaway is that PLC cybersecurity often comes down to basic protection. Do not expose PLCs directly to the internet, change default passwords, secure remote access, and protect every entry point into the control system. One major reason this can happen is poor control of access points. Access points include HMIs, engineering workstations, remote access tools, switches, wireless connections, USB ports, and external network links. If these entry points are not controlled, attackers may use them to reach the PLC or the devices connected to it. Protecting access points is just as important as protecting the PLC itself. If the entry points are weak, the rest of the system becomes easier to reach. Now let's move into the protection strategies. The first protection strategy is to secure the network itself. PLC networks should be separated from business networks using segmentation and firewalls. Only necessary communications should be allowed between devices. Industrial traffic should be monitored for unusual behavior, and remote access should be tightly restricted and authenticated. These steps reduce exposure and make it harder for attackers to move through the network. The next strategy focuses more directly on devices and data flow. The second protection strategy is to secure devices and data flow. Organizations should control who can access engineering software, who can change PLC programs, and who can connect to industrial devices. Strong passwords, role-based access, backups of known good logic, and careful change management all help protect the data flowing between inputs, PLCs, and outputs. These practices make it easier to detect problems, recover from incidents, and maintain safe, reliable operation. Now let's take a closer look at why access points deserve so much attention. Every access point into a PLC system can create risk if it is not properly controlled. Common access points include engineering workstations, HMIs, remote access tools, network switches, USB ports, and wireless connections. If these entry points are left unsecured, they may allow unauthorized access to PLC programs, device settings, and industrial data. A single weak access point can create a pathway into a much larger control system. So what could happen if someone gained unauthorized access? Unauthorized access to a PLC network can lead to serious problems in industrial environments. PLC logic could be changed, machine operation could become incorrect, communication between devices could be disrupted, and production could stop unexpectedly. In some cases, equipment may be damaged and safety risks for workers can increase. In PLC systems, one weak entry point can affect an entire process. That is why technology alone is not enough. Workplace habits matter too. Cybersafe PLC operations depend on good workplace practices. Employees help protect industrial networks by using strong passwords, avoiding shared logins, following approved access procedures, reporting unusual activity promptly, documenting program changes, and using removable media carefully. These everyday actions reduce risk and support safer operation. Good security practices depend on people as well as technology. All of these practices support one larger goal: protecting data flow in the system. In a PLC system, data must move safely and accurately between inputs, controllers, networks, and outputs. To help protect data flow, organizations should segment industrial networks, limit access to authorized users, back up known, good PLC programs, monitor for unusual activity, and manage changes carefully. When data flow is protected, systems are easier to trust, troubleshoot, and maintain. Secure data flow supports safe, reliable, and efficient industrial control. That brings us to the main idea you should remember from this lesson. PLC cybersecurity is not only about protecting hardware, it is also about protecting communication protocols, network paths, and access points, because inputs, outputs, and controllers are connected through industrial networks. Secure data flow is essential for safe and reliable operation. Protecting the network means protecting the process. Now let's wrap up the lesson. You have now completed Lesson 2 on PLC network vulnerabilities and protection. In this lesson, you examined how PLCs communicate in networked systems, how protocols such as Ethernet/IP and Modbus support industrial control, the vulnerabilities in PLC networks, and strategies to protect those systems. As you continue through the course, remember that safe automation depends not only on good logic and hardware, but also on secure communication, controlled access, and responsible workplace practices.